Good afternoon. My name is Michael Smullen. I'm with the SSD team for Samsung, the world's largest maker of solid-state drives. And I'm here to talk about solid-state storage innovations fueling the public cloud. If we think back even just a few years, this was the basic building block of cloud data centers. This is the 2.5-inch SATA SSD. It's a very simple device, and it was very effective. It became popular because it leveraged the low-cost, high-volume supply chain of notebook PCs. This allowed for very inexpensive drives, and more importantly, the ability to produce at cloud scale. But today's SSDs have evolved in several ways and continue to evolve. Three of the ways I'm going to talk about today are speed. The throughput and latency of today's SSDs is better than ever. Size is being rethought at the system level, so we can now manufacture SSDs more efficiently without constraints of legacy technologies. And smarts. SSDs are evolving from simple block storage devices into intelligent subsystems, which can also carry the weight of computing. Let's start with speed. Serial ATA has been with us for 15 years now. It started with a simple 1.5 gigabit per second link, which was enough for any hard disk drive. But as SSDs began to use SATA as their main interface, the interface was repeatedly evolved to higher throughput speeds and now sits at 6 gigabits per second. Unfortunately, this is the end of the road for SATA. There's no additional standards coming to go faster. And at the same time, the NVMe command set is much more efficient and provides much lower latency than SATA could. And at the same time, the PC supply chain has changed. The 2.5-inch SATA SSDs that were intended to have interoperability with 2.5-inch hard disk drives in notebook computers have faded away as consumers demand a thin and light experience that can only be provided by this, the M.2 SSD. And as notebook makers adopted the M.2 SSD, they also decided to adopt the NVMe and PCI-Express interfaces, since they had given up compatibility with 2.5-inch hard disk drives by going thin. This has led the supply chain to change beneath the feet of the cloud data center. And so these dynamics, combined with the high purchasing power of cloud data centers, have made NVMe the dominant standard. In fact, this occurred in the second quarter of last year. NVMe SSDs are now the dominant interface for server-attached SSDs. Many of you in the cloud space may already know this, but some of you in the enterprise space this may come as a surprise. It's already happened. NVMe is the dominant interface for server-attached SSDs. Next, let's talk about size. SSDs had traditionally had two form factors for NVMe. There was an M.2 form factor for servers, which was similar to a notebook PC SSD, except that it was longer at 110 millimeters. This is a very small form factor and allows very dense servers to be built with it. The other form factor that's popular today is the U.2 SSD. U.2 SSD is a 2.5-inch drive physically. And so it has the advantages of having higher capacity with more room for NAND flash inside of it. And it's also designed to be used at the front of a server where it can support things like hot plug and get the advantages of front-side cooling. But today, more and more people are asking the question, what if we did away with the legacy of notebook PCs and 2.5-inch drives and rethought how we designed SSDs for server, especially one-use server. These new flash-native form factors can combine the best of both worlds. They're small in size, like an M.2 SSD, but by slightly widening them from 22 millimeters to 30 millimeters, 2 rows of flash media can now be placed instead of 1, greatly increasing the capacity of the drive. These drives are also designed from the beginning to support hot plug, a feature that wasn't necessary in M.2 because it started off in notebook PCs. And these drives can be placed at the front of a server where they can take advantage of front panel serviceability and cool air from the front of a server. So by combining these 2 form factors, you get the best of both worlds, best of U.2 and the best of M.2. And when you start to look at it at the system level, you can see the density advantages. Compared to the very common 2U24 drive system, you can get a 3x improvement in density, which comes from being able to fit more drives across the front of a server and from being able to do it in only 1 U of height. And the advantage is even more extreme when you look at a 1U server, which is constrained by 2.5-inch drive dimensions. So with NVMe firmly dominant in server data centers, it's time to rethink the form factors and consider using flash-native form factors. Now let's talk about smarts and how they've evolved, how SSDs have evolved to become more than simple block storage devices. Data movement has always been a challenge. It's hard to imagine it now, but moving 5 megabytes, yes, megabytes, used to involve multiple men pushing, pushing a drive along this ramp, right? And in today's cloud data center, Amazon Web Services has introduced Snowmobile to speed the data ingest process. And in the future, as we have more and more data generating intensive applications like autonomous vehicles, we're looking at more generation per device, more devices, much more data. In fact, one estimate I've seen is there'll be 7 million fully autonomous driving cars in 2025, each generating 4 terabytes a day. That is a lot of data. And this data movement challenge has an analogy inside the servers of today's cloud data center. How do you move all of the data for analysis? And to talk more about that, talk more about computational storage, which is an approach to this, I'd like to invite on stage Dr. Pankaj Mehra, Vice President of Product Planning for Samsung Electronics.
Thank you. Michael, thank you. Let's get this mug shot out of the way. So think about how we process data today. So all this data, some of it is processed at the edge, quite a bit of it. But I routinely talk to customers who already have an exabyte of data in their data centers. And not just in their data centers, in particular data lakes. Some customers I talk to have double-digit exabytes in their data lake. Okay? It's no longer like just imaginary future numbers. Okay? How do you ask an ad hoc question against this kind of data and get an answer within minutes? So you don't get those answers by moving all that data out and funneling it into CPU root complexes or into the front of by 4 or by 8 interfaces of FPGAs. Because we are going to need 24, 48 devices, 36 devices in a server. And if all those things start funneling data out just to throw away 80, 90% of the data after the first test, that's a bad way from a power, performance, and every other point of view, right? So this is where we are at right now. The picture on the left shows how we do things. We compute by moving data, okay? And The picture on the right says that we could potentially respect the gravity of that data, especially as it starts to scale to numbers which are serious and measured in exabytes. And instead, sometimes if we have lightweight compute, like simple filtering questions, or aggregate questions like calculating min, max, average, or any other first, second, third order statistical moment on that data, or doing dot product, or doing volume weighted average price, or some other lightweight processing on that data, we shouldn't move that data. We should send the computation to the data and get the 2 or 3 numbers that we are really interested in. Okay? You can think about the same way for search. You can think about the same way for genomics and other applications. Okay? So what we did is we engineered SSDs with internal processing, an internal data path, an internal working memory, so that as you add data, you add processing capacity and you add processing bandwidth. Okay? So we are people who believe in learning by doing. The first device that we built is an add-in card. And we built this within 7, 8 months of actually starting the program. So I joined Samsung in December 2017. By October, we had announced it. Actually, by June, we already had these prototypes last year. And we've been busy doing internal and partner proof of concept workloads on this to see if the idea works. Okay? So what we did is we worked with a hedge fund. The hedge fund gets stock ticker codes from exchanges around the world. And these things go in and they sit in filers and they have half an exabyte. This is the second largest hedge fund in the United States. Half an exabyte of ticker data. What do they want to do? An analyst wants to calculate a custom pricing formula because they don't like just opening and closing price of a stock. Okay? You do that using this new smart way. You can do this 3, 4 times faster than the old way. Okay? Another example, very traditional, you take MySQL MariaDB variant, you take an old data warehousing benchmark, which is known to be IO-intensive workload, like TPCH. We know that in TPCH, filtering removes about 87% of freshly fetched data. So you have 2 choices. You can do TPCH data warehousing workload, either by pulling data out of the SSDs, taking to the processor, polluting caches, crowding out root complexes, moving data over QPI if your PCI and accelerator are on the opposite sides of the 2-socket or 4-socket server. Or you can leave it in the SSD and process it there. Okay? When you process it there, your entire query set for TPCH runs 3.5 times faster. Another example, take open data sets. In this case, we took airline industry data. We are running a live demo in the Xilinx booth, and you can see more about this data set at the Samsung booth as well. So when you go from a traditional SSD to the first smart SSD in your server, you see a 4x acceleration. Then you double the number of smart SSDs in your system, your performance nearly doubles. Double again, your performance doubles again. We are seeing the beginnings of scaling past the roof lines that the funnels in today's system architecture exposes. The next step for Samsung is to take it to customers and to do the same thing that we have done with internal and partner POCs, to do this with customer workloads in customer context. Okay? That's what we are doing about now. And we have a roadmap where we are now enabling customers to take either server-centric workloads, like are shown here, okay, for databases, or storage-centric workloads, which I'll discuss next, at scale. So as you add data, you add capacity, you add bandwidth. Okay? So what is shown here is what happens with Spark. So the way we do distributed computing today for data, I call this idea sprawl out. Okay? Every time we have 4 or 8 SSDs, a server chokes up, we add another server, then it chokes up again, we add another server, then we add interconnect, we have to add racks, costs keep mounting. And if data grows at the rate at which it's growing, we cannot afford to have costs grow at the same scale. So the basic idea here is, can we miniaturize clusters into servers and servers into devices? So think of the SmartSSD as basically a subsystem that acts more or less like a storage engine. You take the basic query processing stack in which you are going to decrypt, decompress, and then filter and aggregate the data, and push it down into the FPGA that we have placed near the device. Okay? And so the interface, you can now talk to it arrow. You don't have to talk to it block protocol. It is as efficient as protocol buffs is in a Google cluster or arrow is in a modern non-Google cluster. So these things, they talk to you just like other nodes in the cluster do, and you basically get heterogeneous clustering. You can imagine the same kind of server chassis that Michael was showing now behaving like basically a Spark cluster. And we see the evidence of that when we run Spark workload on these things. You can run a much larger number of executor threads on a server that has smart SSDs than you can on a server that has traditional SSDs. Okay? So no more funneling, and you do processing near the data. Second thing is, you can do the same thing to your storage nodes. So just like I showed you for compute nodes, in storage nodes, what you're trying to do is you're trying to go for density. And the challenge you run into when you use SPDK or somebody else's network protocol termination is that as the number of devices grows because of density, you choke at the front end, okay? Because of the decompression you are doing, or deduplication you are doing, or compaction, or any other kind of storage processing workload having to do with software-defined storage or thin provisioning or anything else you want to do in your storage stacks. So the idea here is the same thing. Your stack, storage stack tends to be a little bit thinner, okay? And you probably want a little bit lighter cost of computation because you're packing more devices in the servers. You probably don't have as much power to burn in those FPGAs. But you push that stack down into the same FPGA. This time that FPGA, instead of becoming a database storage engine, it is now your storage processing offload, okay? And you can switch these personalities in a few milliseconds. Modern FPGAs can afford partial dynamic reconfiguration very, very quickly, okay? So you deploy one infrastructure, and then you can commission it to, even if like you had a machine learning use case, a new detector you learned. So it can be something completely different than either storage services or data services. You could just take a new detector that you have learned using CNN, push it down after compiling the network, and all of a sudden your FPGA is now a machine learning engine, or something else, okay? So that's the idea, is software programmable infrastructure that has the flexibility and programmability of software, but the speed and parallelism of hardware, okay? And doing this at the speed scale of data. So what we are doing is we are also engineering past the add-in card form factor, making devices that you can actually reasonably populate in a 24 or 48 device chassis. So the next thing we will be building sometime later this year is a U.2 form factor device, okay? That will do the same thing. So we are busy miniaturizing our own miniature server. And you can imagine that right after this, we'll be going past these initial workloads. And like I was saying, you know, it's limited only by your imagination. So I'm sure you see something over here that you recognize in your own situation. And then the way we have engineered this device, it basically exposes 3 PCI physical functions. 2 of them that resemble what a standard FPGA exposes, and one that basically is a standard NVMe SSD. So if you know what to do with the standard NVMe SSD, you can use our smart SSD right away. If you know what to do with an FPGA, a Xilinx FPGA, you can use this device in your familiar SDXL or Vivado flow right away. You can develop to that flow, you can deploy to that flow, and we have partners who have already done this. So we have partners who have done MySQL and Spark integration, like I showed in the first few slides. And we have additional partners now working on Postgres, Cassandra, and other integrations right now, okay? And we'll be going beyond these databases and storage services to, like I said, video, AI, ML, and other use cases. Okay? So you can imagine, the accelerators that I list on the left are, you're only limited by your imagination as to what you want to do there. So that's the end of my planned comments. I've left you some pointers here. They will be available as part of the slides as well, or you can take a picture as you already are. I have two sort of things that I want to call your attention to. First is that if you have a compelling use case, like you're drowning in data and your processing is not keeping up, come and talk to us about your use case. You're not alone. There are many, many customers across science, across very traditional storage, data lakes customers, data analytics as a service customers, storage as a service customers who are working with us right now. I'm sure there is some learning that we can share with you that will help you get started. Second thing is that this product is still in its early phase. By working with us, you can have an influence on what the real product from the top SSD vendor in the world will be. So help us shape both the standard that we are working on in SNIA with other companies, as well as the next generation product that we are developing in-house. And we'll make available these things in various kind of clouds and colos, so you can play with it if you have a suitable use case. Michael, you want to add something?
I want to thank everyone for coming to our session. We have more to show you on the expo floor, both in the Samsung booth and in the Xilinx booth. The Xilinx booth has a live demo running SmartSSD for data analytics. And in the Samsung booth, we have a number of displays, including SmartSSD and also servers based on flash native form factors. So please come by and check it out, or contact me after the session if you want to learn more.
Thank you.
Thank you very much.